So to set up our discussion of electric forces and Coulomb's law, let's very briefly think about what we already know about the law of gravitation. So we said if you've got two particles, so mass m1 here, mass m2 here, they're separated by a distance r, that the gravitational force that's going to be exerted between these two particles basically has three properties. It's directed along the line joining the two particles, it's always attractive, and it has a magnitude that's given by this equation right here. So we know that the magnitude of this gravitational force is going to be proportional to the product of the masses over the distance squared, the distance between them squared, and the constant of proportionality that's going to convert from that quantity to the force is g. So now let's come and look at Coulomb's law. So what Coulomb's law tells us is that an electric force between two particles with charge q1 and q2 separated by a distance r has the following properties. And so the first thing you'll notice right away is that there are actually a couple of options here. And so the properties we've got is, well, all of these forces, in this case it's attractive, in this case it's repulsive, all of these forces are directed along the line joining the two particles. So again, here's our line, that our particles, our charges lie along, and the forces are always directed along the line. Obviously, it can be either attractive or repulsive. And so this is why we actually need two different types of charge. We said that mass, the gravitational force is always attractive, so we only need one type of mass to explain that, and so that's why we say mass is always positive. But to explain what's going on with the electric force, because it can be both attractive or repulsive, we actually need two types of charge to explain that, and so we've chosen to call one of them positive charge and the other one negative charge. And then 3 is the magnitude of this force can be written as follows. So notice it has a very similar form that our universal law of gravitation does. There are a couple key differences. One is now these are charges rather than masses, and this is the absolute value, so we'll come back to this in a second. This is the absolute value of those charges. We still have the distance squared, and now we have a new constant of proportionality. So this is called our Coulomb's constant, and it has a value of 8.99 times 10 to the 9th. And again, what it's going to do is it's going to take a charge squared, we know charge has units of coulombs, over meters squared, because that's a distance squared, and give me back something in Newton, so it has to have this unit of Newton meter squared per Coulomb squared. Okay, so what does this expression tell us? Well, again, part of what it says is we know that all forces are interactions between two objects, and so this tells us that electric forces are interactions between two charges, so Q1 and Q2. And this means that objects feel an electric force because they have charge, right? So if you have an uncharged object, it's not going to feel an electric force. The larger the distance between the two objects, the weaker the electric force between them. So again, because I've got this distance between them squared and it's in the denominator of my expression here, that means the larger I make the distance, the weaker I'm going to make the force, and it happens to be in a very particular way. So if we double the distance between our 2-point charges, then that's going to cut the electric force to 1/4 its initial value. So again, this is another inverse square law, just like the universal law of gravitation. Well, as a general rule, electric forces are much stronger than gravitational forces, and again, that comes down to the value of that constant. So our gravitational constant was a very, very small number. Coulomb's constant is actually a fairly large number. It's basically 9 billion. That's a pretty big number. So relatively speaking, gravity's weak, but electric forces are relatively strong. And that you can have significant electric forces without having a whole lot of charge. We said that because G was so small, to have significant gravitational forces, you needed a large amount of mass. I don't need a large amount of charge to build up fairly significant electrical forces. Now, the Coulomb's constant here, K, is actually related to another fundamental universal constant that we'll deal with. So K can also be written as 1 over 4 pi epsilon naught, where epsilon naught is called the permittivity of free space, or the electric constant. It's also called the electric constant. And it has a value of 8.85 times 10 to the minus 12. And again, basically all we're doing is, since this epsilon naught is on the bottom here, it's got to give us our Coulomb's constant when we multiply it in. You'll notice that the units here are just the inverse of the units here. So K and epsilon naught have to have, their units are just the inverse of each other. So the nice thing is, we're going to sort of go back and forth in terms of using these fundamental constants. But pretty much if you can remember one, you can remember, you don't ever need to worry about remembering the other because it's very easy to calculate. Alright, and then the last thing to pay attention to is, of course, all forces are vectors, so electric forces must be vectors. So sure enough, this has got to be a vector. So there are a couple really important details that we're going to have to remember when we're working Coulomb's law problems. The first one is, because these are vectors, the signs of the components of your electric forces are determined by your choice of coordinate system. So if you have a force that points to the right, and you pick to the right to be the positive direction, that force has to have a positive, or that component of the force has to have a positive sign, regardless of what's going on in here. So you'll notice that when we talk about this being the magnitude of electric force, the magnitude of any vector is always positive. K is a positive number. R is a distance. That's a positive number. Our charges can be positive or negative, but that's why they're put inside these absolute values, because our magnitude has to be positive, because the sign that we need to use with our vector is going to be determined by r hat. What's the direction the vector points, and then what is that relative to the coordinate system you've chosen to use. And so that's one of the big differences between working our universal law of gravitation problems versus our Coulomb's law problems, is students are going to want to make a mistake in terms of how to deal with these signs of their charges. And all we're going to do is just say, well, the charges for our vector problems, the charges go inside absolute values. The other thing, of course, to remember is that this means that electric forces must be summed as vectors. So we're going to end up working very similar problems to what we did last week, where we were summing gravitational forces. Now we're just going to be summing electric forces. And so again, we'll need to keep track of the direction, r hat, the direction all these vectors point, as we're doing our summation.